All right. Thank you, everybody, for joining. I'm Victor Boutte, software engineer over at SimSpace. And today I'm talking about Intro to Functional Programming in TypeScript. And this talk is a lot less about TypeScript and more about functional programming concepts, but I'm going to do the best I can in the short amount of time that I have to cover concepts and practical use cases. So I wanted to start off by talking about building software at a very high level, some of the things that we expect, right? So we have a main product or service that we offer. Typically, it's some type of solution that we've identified we have for a problem that exists, and we hope that we can target a certain audience that is willing to pay for that solution. This product is made of multiple features that make up, the product or service we're offering. And as I said before, there's an audience that we target, and there's evolving requests for new features. And it's not just new features, it's existing features that need to be tweaked and polished throughout the application's lifecycle. And then we have a team of engineers that support the software, from front-end devs to back-end devs, DevOps to ensure that the infrastructure is up and running as we expect. And we have quality assurance engineers who are testing to make sure that the product is what we say it is before we give our final stamp of approval and ship it out to the customer. So product maintenance. As new feature requests come in, we break up the ask into incremental MVP deliverables. So we might have this really huge feature that we're pushing to, but what we immediately do as teams is we try to identify the least amount of work it'll take to get an MVP out the door and just incrementally start to build upon that. And as the complexity of our application grows, so does the code base, right? And we try to combat that by reusing logic and components to minimize the overall footprint and time spent, at delivering these things. And it could be said that reusable code, generally takes more time up front because you're trying to generalize and abstract away implementation details, but it ends up paying off in the long run because you've granted yourself now, these different pieces of code that you can use throughout the app. And typically what we do is we name functions and variables as they relate to specific features and domains of the application. And this is where things can get really hectic very quickly because we start trying to make the code mimic real world scenarios, and it just doesn't typically happen like that. So you have like this applicate this part of the app that's specifically for the financial section, and you have functions in there that's like finance converter or finance validation, where we're piping through this data object and running this validation check on it. But just by looking at the function and variable names, you can't really tell what the hell's going on or why it was named that, what other parts of the application it's touching. And things get hairy very quickly, like I was saying, because that makes things harder to maintain. You're scared to touch things. It's like old school CSS where you're afraid to pull out one selector and then the rest of the application all of a sudden looks really weird. To help get away from that, functional programming is here to, or has been here for a long time, to help rectify these issues. And we'll just start off with this very simple definition that I put together, which is that at its essence, functional programming is just about programming with functions, but more specifically, it's the act of building single responsibility functions or algorithms that are composable, pure, and reliable. And we're going to unpack what that means. Whenever we combine these things, the functions handle data manipulation and business logic of our software. And at an even higher level of abstraction, we can say that functional programming is rooted in a specific branch of mathematics known as category theory. And because of this, when we adhere to such a mathematical paradigm, we inherit a wealth of power and flexibility that make our functions more resilient and our applications better to use and maintain overall, because we're not consistently reinventing the wheel for these very specific like domain related issues. We'll start by saying, pure means that a given function has no observable side effects and that it's solely responsible for taking in a single input and computing its corresponding output. And furthermore, we could say that an observable side effect would be anything that happens outside of the scope from original computation of transforming that input to output, as in calling out to a database, making a network request, log into the console, changing some value of some variable that lives outside of the function. This doesn't imply that, in applications built with FP that there aren't any side effects. Side effects are inevitable to a degree in which your application really wouldn't be very useful without them. But in functional programming, there's ways of modeling these side effects to allow us to contain these behaviors, and it makes our applications more predictable. And I'll explain, how we do that, especially as it relates to side effects, because it's very, interesting. How do you make a side effect pure? All right, so when a function is pure, we say that it's reliable, also known as deterministic, where a plus b equals c. We can pluck out the function a plus b and replace it with the computer result c, and the rest of our application would continue to work as it did before. So for instance, like I was saying before, if something's not pure, there's a number of things that could be related as to why it's not pure. But one of the worst things is that, within a given function, out of nowhere, there's this other variable that lives outside of it, and we just mutated it. Whenever we do that, it's very, very hard to track that mutation and understand why something changed somewhere else because of your impure function. So we avoid that at all possible costs in functional programming. Lastly, composable functions are functions that can be reused and combined to create more powerful functionality. And the reason why I included these graphics here is, I find a very helpful analogy to think about as data flowing through our application, right? As a series of interconnected pipes that transform input to output in a way that makes the data more accessible to the users of our application. And this idea of integrating data in our app is known as data plumbing. And how these pipes connect can be thought of as composition, where we reuse copies of the same pipe to orchestrate data plumbing in different parts of the application. Really, in functional programming, composition is king, right? Because it allows us to take bigger problems, chop them up into smaller problems, and solve for those, and then combine the results and reuse those solutions throughout the code base. I promise we're fixing to get on to more practical examples, but I needed to cover these three fundamental concepts. Concepts come from category theory. So on the far left, you'll see the type class names, and then in the middle, the laws that are associated with those type classes. And then in the far right, the power that these laws and type classes unlock to you. And again, this is math that predates everybody on this call by a lot. And it's beautiful that it relates to programming in such a way that, it's easy for us to model our functions and algorithms, that adhere to these laws. So we're going to start at the top with a magma and say that it's a closed binary operation, meaning that given two types, when you combine them, the yielded result is of the same type. So if you combine two strings, the result of that combination is going to be another string. If you combine numbers, like the example here, 4 plus 2, it's going to yield 6, which is the same type of number. And the power that unlocks this composition, you can use this, throughout the app. You can take out chunks and compose them with one another, which leads us into the next thing, which is a semigroup. So it is a magma that there's a closed binary operation, and it's associative. And what that means is that as long as the inputs maintain the same left to right order, you can group them however you like. And what's beautiful about that is that it unlocks parallel operations. So, you can think of running through a list of a bunch of records, and you need to combine them all, or you need to go in and like sum up certain fields that it's just going to be very computationally heavy. So if they're all semigroups, you can chunk up the work amongst like different threads, and then in the end combine all of the results and get the same result as if you just ran it all on one thread. So this unlocks very like fast algorithms for you. And then a monoid extends this notion by providing this identity. And what an identity is that saying, like in the absence of a value, we can guarantee an initial value in its place. Back up at the top real quick, I just want to look at the 4 plus 2 equals 6. The plus there is pink because that is the magma. That is the binary operation, that addition sign. For an array, you could think of a concat as being the operation that combines things. And semigroup, also you could see the brackets or braces are same color as a semigroup because that it's about the grouping. No matter if you group 4 plus 2 or you group 2 plus 3, it's equivalent. And then monoid, the example is actually wrong here. Well, actually, it's fine, but for a monoid, addition, I believe, is 0. So anything plus 0 gives you back the same number that you started out with. And then for multiplication, it's 1. So if this was 4 times 2 times 1, then that would be the same. Because anything times 1 is equal to itself. Enough with the concepts, right? We're going to look at some code for the following 2 practical examples that you can most likely see in any application you work on. The first one we're going to look at is merge strategies for duplicate customer records. And to do this, we're going to leverage semigroups, monoids, and some other things that I might not touch on, but I'm going to get into that. And then the other example that I wanted to cover is sequential network requests that depend on one another. And we're actually going to be using task either to do that in conjunction with something else. Let's go ahead and hop into the code so you guys can see what's going on. Oops, let me go ahead and comment that out. All right, so what we're going to do is start off in the merge strategy example. And we're going to start by looking at the type here. What is a customer? What makes a customer record? And for this example, it's 5 things. We have a name for the customer. We have a list of their favorite things or collection of their favorite things to do, when they were registered, and the last time that they were updated. And then lastly, have they made a purchase on our platform? Here, we're going to go ahead and define what the strategy looks like. And for this example, we're just comparing 2 things and combining those 2 things into one record. So for the name, what we want to do is we want to keep whatever name is longer between the 2 records that we're merging. And that's essentially what's going on here. We have this get join semigroup, which is going to keep the larger thing of the 2 things that it's joining. And inside of that, we're composing these 2 functions where we say, this ord number is how you order numbers. And then this contra map you can think of as a pre-hook to values going into the operation. So if I said that for an array of strings, I'm going to map over each one and capitalize the strings. That's like a post hook where as the values are leaving, you're transforming them. Contra map allows you to do it on the way in before some other function runs on that. And what we're doing here is we're pulling out the length of these strings so that they can be compared to one another. And then from that result or evaluation, we can get the longer name or the longer string. Next, we're doing an accumulation of favorite things, and we're using this get monoid. Sorry, I should have backed up and showed you. I'm using this get struct semigroup, and what it does is we provide it an object where for each property, we define how that property merges. All right, so going back, same thing, we have this helper here, get monoid, where we're saying we're going to combine these things, and if we don't have a value, we're going to ignore it actually, and not worry about things falling apart. So for instance, if you just had like an empty array and then an array of strings, you could still combine those and get the array that had values in it. All right, and then for registered at, we're going to use get meet semigroup with the ord number, same thing that we did up here. And what that's going to do is just grab the least one. So as it relates to dates, we're just saying the least recent, we want to hold that. So whenever the first record, whichever one registered first, we're going to keep that value. Then for last updated, it's the opposite, right? We want the duality of meet semigroup. So we're going to use get join semigroup, which is essentially the same thing that we're doing up here. We want to keep the larger of the two. And then at the bottom, we have has made purchase, which is a semigroup any. And what that says is if you give me a list of booleans, if any of them are true, I'm going to provide you back a true. If it was semigroup all, we would expect that all of them be true. And if anyone is false, then the evaluated result would be false. All right, so that's it for the semigroup customer. And I'm going to go ahead and show you. I'm pulling it in. And with a semigroup, we can always expect that there's a concat method. Because if you recall back to the slides that I was going over earlier, a semigroup just defines how something combines. So its type class says that there's always a concat method that is associative and is a closed binary operation. So given two customers, I'm going to get out another customer. I'm destructuring off of that, and I'm calling it combine customers here. And I'm providing it 2 records. And I'm going to go ahead and uncomment this so we can see which pieces of information wins in the merging strategy. And we can see that here, Bobby Axelrod won because the length of his name is longer than the other one that it was being merged in with. Favorite things was combined for one full list of favorite things to and then registered at and last updated worked as you would expect. Same for the Boolean down here. One of the things that I want to take a beat and talk about here is that the naming. So I've named this, yes, customer is specific to a certain domain in my application, but I prepended it with semigroup because there's this, expectation of what that encompasses. So when somebody who else is, familiar with what a semigroup is, or maybe they weren't, but they've been onboarded in the process and they have a vague understanding, whenever they see this, it'll trigger something in their head and say, that must have, a concat on it. So this makes it easier to reason about in the code or whenever you name things similar to the ADT that they're encompassing. ADT meaning algebraic data type. Move on now to, so this is all good. And we'll say that, the ask was that you needed to provide this new feature that allowed a user to merge 2 customers. But you've realized now that that's not good enough and that you need to be able to merge a list of customers. So it could be any amount of customers. Let's say for some reason there was 12 duplicates, but we need to use this merge strategy 12 at one time. So what we'll do is we'll go ahead and create a customer. Now, first what we'll do is for the name, we're going to describe our own merge strategy. So longest string monoid. And again, you have in a monoid a concat method because you can combine things. And then you have this initial value here. Typically, it's called empty, but it could be called other things. So anyways, we're calling it empty and we're saying if we need to, we're going to fall back, or sorry, we're going to use an empty string as an initial object. Favorite things, same as above, we're using get monoid. Registered at, we're using get meet monoid with this bounded number. And I won't go too far into detail about what that is, but essentially you can think of it as if no registered at date was provided, then I'm going to use the one that I'm comparing it to. Same thing for last updated. Same here for has made purchase because it's a monoid any. If no Boolean is provided, it's going to default to false, I think. Monoid any, yeah, if there's not one, or maybe it's true. I always get that mixed up. Just a note though, I will say that name and favorite things doesn't actually work as I would expect because What I would like it to do is if I didn't provide a name, I want it to default to an empty string. And I could do that, but up here I'm deliberately saying that I expect there to be a length on them. So I say that to point out that these two merge strategies could be better implemented. Now, before we go and look at the results, you could see here, I'm giving it an array of customers instead of just two. And we're going to throw all of these together and see which ones win. So whenever we come back here, we run it, and I'm going to actually uncomment both of them at once. So you could see this was the first merge strategy, which is 2, and then this is the third. And real quick, if I jump back over here and I actually nix all of this information, it still works. So this is good, right? Because our merge strategy didn't fall apart and cause some white screen of death because somebody was halfway updating a record before the application stalled out on them. So this is what we want, this type of resilience. All right, so if we go back, I wanted to point out this this fold, what's going on here. So fold is this curried operation where we start with an initial value, and because it's a monoid, it knows in the presence of absent values what to fall back on or what to use in place of as the initial object whenever you're merging in this collection, the second argument that you provide. It knows how to merge all of those together. And that's it for semigroups and monoids. I know that I'm flying through these things, but just for the sake of the time that I have to cover them all. Oh, and I'm just going to point out that this code pin is going to be available to you. Sorry, this code sandbox is going to be available to you in the chat and in the slides at the end of the talk. All right, so now we're going to go over and look at network requests. We're going to start off with this very simple traditional fetch call where I'm using JSON placeholder to fetch a list of users and parsing the response and then logging out what that response is. And if something fails, then I'm going to log that out as well. So if I come back here and I uncomment this, you can see that the results are what you would expect from the API. All right, so now let's say that we got this ask where they're like, okay, good. Whenever somebody enters our dashboard, we need to get all of the users, and then we want to fetch the users, a single user based off of the first one in the collection, get more information about that person, and then we want to make another call and we want to get all of the posts that are associated with that user. So in the traditional chain of network requests, a lot of people refer to this as callback hell because it's not a nice place to be. So you can see you start with this fetch. Whenever that result gets computed, sorry, let me go back and actually uncomment it so that we can talk through and see the examples on the right or the actual response. So first it's fetched all the users, it's gotten a single user, and then it's got the post related to that user. And just as you would expect, we get the first response, we parse it, and then we use the result of that response to push through to the next fetch where we pull off the ID from the first record, we parse that information, and then we pass that through to the third and final call. And along each step of the way, we're logging out to the console what's going on here. Now, in a real application, you would be storing this somewhere in state management. And yeah, so there's a couple of things wrong with this. Number one, it's hard to reason about whenever you first look at this. There's a lot of overhead cognition of trying to figure out why it's calling things in a certain order, what this has to do with the rest of the code, if something fails, we only have one single catch down here, and we don't know where along the way, it failed. Hopefully that error would bubble up, but there's a chance that it wouldn't. There's ways around this that you'll see we use in the next example where we use async await. But yeah, so essentially this is what things used to look like before async await came about and really helped people reason about their code. So we're going to go ahead and comment that out and bring in the async await example. And again, on the right, you can see it's the exact same response where we first get all the fetch users, and then we get the single user definition or response, and then all of the posts related to that person. So if we look at this code, we have, at first glance, we have this let variable up at the top, and immediately you might think like, what the hell's going on there? Why are we doing that? So we have to further look down into the code and drill in and again, keep this overhead, cognition of what's going on and why. So anyhow, we look at the first call, we make it, we parse the response, and then, oh, okay, I see. So we assign that let with the response of that, provided that this worked. And then we log the fetch all users with the response in it. And if it failed, we throw this failed to fetch users. All right, so next we go down and we see that we have this guard here. This is contrived in a way that's not very helpful outside of this context. We say if all users is available and the first user's ID is less than 2, then go ahead and proceed. And the way that we should think about this for the sake of this example is that we're putting this guard in place for people who should have the privileges to make the next call. So for instance, if we go back to the example of logging onto a dashboard, you might only want to call the next 2 network requests if the user is an admin and they have privilege to that information. Because what you don't want to do is just eagerly make all those calls despite the role of the user, because while you may be able to not present certain things in the UI on a conditional basis of the role, you're still making the network request. And if you have a savvy user, then they can, inspect the network tab and see what information is coming back. And if, for example, that has some private keys or something, then that could really put you in a world of pain that you don't want to be in. So back to the example, we have this guard in place to prevent that from happening. And it's better than the dot chaining fetches that we were doing above, but it's still convoluted. So we make the next call with information from the first one. We parse that information, log it, and then if things fail, we provide that error message. And then down here, same thing as above. So how can we get away from this with some functional practices? Remember what I was saying earlier, how we try to model these side effects in a way that their behavior is contained. And we do that by making these side effects lazy so that they're not immediately invoked. And with these, they are immediately invoked, and it becomes harder to test these type of requests. And it's also harder to predict, like what's going to work, what's going to fail, why things failed. So let's see what we could do to make this a little bit better. So first, what we're going to do is start off with this safe fetch, where you'll notice above there was this pattern of we were looking at a specific URL, fetching the information from that URL, and if things fail, we wanted to provide an error message. So we've modeled this generic abstraction that says, okay, given a URL and an error message, we're going to try and make the call. And if it fails, we're going to catch that and do something with the error message. So this task either is representing how things can either succeed with a array of users, or they can fail with an error of the message that we've provided in its presence. And what's cool about this is that immediately this isn't invoked. So I'm getting this from FPTS up at the top, this task either. This is the latest edition of the library. And previously, there was this this method on it that you would invoke, like right here. You would do dot run. Okay, you do dot run, and whenever you called that, then it would invoke. So what you would do is you just leave it as is like this, and then at the call site, whenever you're ready to actually perform the execution, then you could run it. And by stalling the function invocation like this, it allows you to compose these functions together, manipulate the data in this composition pipeline before you actually perform the side effect. So it's easier to test. It makes it pure in the sense that it's not immediately invoked, and you have um, this consistent result because it's curried and because it's not eagerly invoked. So to look at that, I'm going to comment out this and look at that call by itself. So again, same as above, the simple fetch up here, it's the exact same response. But you'll see here, we have the function invocation where I said previously this was run, but that no longer is a thing. It is just actually invoking the function. And then in here you have a handle on what that result is. So because of point free, you don't have to explicitly type this out, but to show you what that looks like, this is what's going on under the hood. And you'll see in the right hand corner, or sorry, the right side of the screen, the same result is being logged out. And if I hover over this with TypeScript, you can see the type that this is outputting, which is an either, it's an error or an array of users. Now, just a small tangent to talk about either. Either is an algebraic data type that has either a left value or a right value. And convention dictates that the left value is typically a failure or an error, and the right value is a success. So what this looks like inside of the fold is something like this. So this is called on error, and you pass it through like that, or in success, you pass it through like this. Now, again, for those who aren't aware, and you can see here, the value is the same, that it's being logged out. But just to show you why I wasn't doing that, there's this concept called point-free programming. So if you have a single argument that goes into a function, you don't have to name it like this. You don't have to use the lambda or the arrow function to pass it through. You could just leave it out, and it will automatically be implied that it gets passed through. All right, so enough with that. I'm going to go ahead and close that out. And now back to the meat and potatoes of this example of making the sequential requests pure and consistent and composable. So I have a colleague of mine, buddy of mine, he created this do notation, which I believe comes from Scala and maybe Haskell, but I think his inspiration came from Scala. Anyways, what it does is we're saying this, we're saying do this task either operation, and then we're going to bind a bunch of calls in order. And what's going on here is that we're building this contextual object throughout these bind calls in order. So first off, we do this bind operation where we say the result of this operation, we're going to call all users info, and then we're doing our safe fetch where we pass in the URL to go and fetch, and then if things go wrong, this is the error message that we're going to kick back. Next up, we do this bind L, and we call this single user info. Now, the reason it's called bind L is the L stands for lambda, in that we don't just immediately invoke it like it is here. We have this this lambda available to us with this object inside that is the context from its preceding bind calls. So if you look at the next example down here, we actually have access to single user info because the one right before it is up here. And before that is all users up here. So this is helpful because, again, we have the sequential stream of network requests where certain things need to be called with information from the one that preceded it. So we pull that information out here, and then we could do our guard check right here to go ahead and get that information out. And I'm going to go ahead and uncomment this before I go further so that we can see what the call looks like. Okay, so we get back a single object where we have all of our information available to us in this nice and tidy object. And again, just to prove that this is working, we pull out a single user at the ID of 1, and each post related to that user should have, a user ID of 1. And it does. Cool. So go ahead and minimize that and jump back into the example because I wanted to explain down here at the bottom, we have that object of context, and we're just spitting that right back out. We could rename these into whatever we want. And you would still, get that back right here, as you would expect. But what I did want to show you is here in the guards. So again, it's the same thing, quote unquote. We're just checking to make sure that the user has privileges. And if they do, then go ahead and perform that safe network request. If they don't, then just return an empty object. But what we do is we wrap it back up in its task either. And to show you that in practice, if I mess up this URL, you can see that it failed with the error message provided here. So failed to fetch all posts for a single user. All right, so I'm going to uncomment that. And I just wanted to explain that the reason why we wrap this empty object back up in a task either is because you can think of these ADTs as contextual objects. Instead of just passing freely, instead of just passing variables freely throughout the application, you leverage these contextual objects because they have type classes implemented on them that give you these functions for free. So like the semigroup with the concat and the monoid with the empty task either has um, this left or right value, and that's kind of like the beauty of these functional practices is that we get to leverage the math behind all of it. Now, again, down at the bottom here, I'm calling, okay, go ahead and invoke the do sequential request. And then I have a handle on its response. And as I explained earlier, we already know what's going on with this fold. And that's pretty much the gist of my talk. But I just wanted to close on the fact that um, so the fact is that as humans we've been building up mathematical methods for thousands of years, and all of our applications pertain to specific domains and they cater to specific audiences. But we can model our applications so that the code it runs on is less domain specific and more general in how it manipulates the underlying data. And as software engineers, we know that requirements are subject to change. There are several reasons why requirements could change at any point of an application's lifecycle. What's important is that we stay flexible so that our applications can scale to accommodate the audience that we're targeting. And to do this effectively, we need to our code needs to be reliable, right? So this is kind of like a callback to the promise of functional programming, where we aim to build these single responsibility functions that are composable, pure, and reliable. And to jump back over into the notes, this is a list of the resources. The code box is here for you to go and play with. And again, feel free to ping me in the Slack channel on ODevs. The article on the do syntax, there's some really cool examples there where He's showing you how to build a validation algorithm for a form object. That's really cool. If you get a chance, go and check that out. And then there's this other one called Getting Started with Semigroups. So the author of the functional programming library that I was using, FPTS, this guy is wicked smart. He has, I think, a PhD in mathematics. Anyhow, he has a full blog series where he steps through like a bunch of these ADTs and type classes, and he gives you practical examples and kind of breaks things down and helps you understand them. His functional programming library is 100% test coverage, so you can look at the type signatures, you can look at the tests to see what's going on and kind of help you reason about. And then lastly, I have my Git on here and Twitter, so feel free to reach out. And again, guys, really appreciate your time and hope everybody's safe and healthy at home, and look forward to hearing from you. Thanks.